Okay, at the end of our last video, this is pretty much where we were. What I have here is the molarity of our acid. Okay, so this is what we can do. We can say point. We can say we have Kb, which is 2.56 times 10 to the negative 9 equals x squared over this molarity we got, 0.0424 m. No, it's minus x, but the x is going to be small. We're going to assume it's small. So x ends up being 1.042 times 10 to the negative 5th molar. Remember, that's the same thing as OH. So that means our OH minus is the same. Okay? And then what we're going to do is we're going to say, well, what's the pH of that? And the pH, or the POH rather, is going to be 4.98. And the pH ends up being 9.02. So lo and behold, we have another point. So at 14.7 mils, we have 9.02 pH. Now that's probably the hardest one to do right there. Now probably the easiest one to do would be at half the equilibrium. So, or half the titration. So what I'm going to do is I'm going to shove that in right here. Half the 14.7 is 7.35. So at 7.35 mils, we have a perfect buffer. So pH equals pKa, which equals 5.41. So we have yet another point here. So there's your three basic ones. Other than that, what you're going to do is sort of fill in. So I'm going to show you what to do maybe at 3 mils. And then maybe what to do at, if we have 25 mils. Okay, so really quickly, this is how you would go about it. This is all stoichiometry at this point. So number 4 will be at 3 mils. 3 mils added. And we're talking about 3 mils of base. So this is what this thing looks like. HA, which is our KHP plus OH minus yields H2O plus A minus. Okay, this is what my initial acid is. And we'll be using that in a lot. That's moles now. This is all moles. And my initial, if I add 3 mils, it's 3.0 times 10 to the negative 4th for OH. Yeah, that's definitely going to be my limiting reactant. So the change here will be minus 3.0 times 10 to the negative 4. Minus 3.0 times 10 to the negative 4. Okay, and then this started off at 0, but we're going to add 3.0 times 10 to the negative 4. So this becomes a series of buffer problems. We can use Henderson-Hasselbalch to deal with that. So we have 0 of this left, but we have 0.00117 moles of this. Okay, now we are dealing with moles, and yes, you should use molarities for the Henderson-Hasselbalch, but it's the same solution, so the ratio is going to be exactly the same. So to speed up this process a little bit, this is what I'm going to do. I'm going to say pH equals 5.408, which plus the log of 3.0 times 10 to the negative 4th, which is our acid, and this will be our, oh, I'm sorry, that's our base, and our acid is 0.00117. Again, I'm using moles here, but the ratio is going to be exactly the same because they're in the same solution. And this is going to give us a 4.82 pH. Now let's see if that makes sense. We started off at the beginning with a solution in 20 mils of water that was 3.27. So after 3 mils of NaOH, 4.82 sounds pretty reasonable. Now I'm going to do one more that has to do with what if we overload it. Okay, so if we put, let's say, 25 mils in. So way at the other end, this is going to be, remember, this thing's titrated at 14.7, so 25 mils of NaOH is going to be way overboard. So when it's set up the same problem though, HA plus OH minus yields H2O plus A minus. And we have exactly the same amount, 0.00147. My OH amount though is 2.5 times 10 to the negative third. Okay, and this is 0. So if we do this, now my acid is my limiting reactant. So I don't have any of this left. That's 0. I have minus 0.00147 of this now, and I had basically 0.00147 of this over here. So in the end, this is what I have. Now, that little base right there, now that A minus guy right here is a base and does add to the overall basicity of this solution. But really, this is what's going to make the difference. It's going to have a much greater effect than this small base over here. So this is OH. It's a strong acid, a strong base. So let's keep that in mind as we do this problem. Now, we just take that, that's moles now. I'm going to divide it by 0.045 liters. There is no buffer anymore. We're not using Henderson-Hasselbalch. There's nothing left of anything. So this is equal to 0.0229 molar. And that is pH. And pOH is like 1.64. pH ends up being 12.36. So we have that point as well at 25 mils. Now, I added a couple more points in, but our graph looks something like this. And if you take a look at it, that's what we started with, half titration, and then equivalence point, and then once we overloaded it. Okay, so that's graph. So that does it. If we scroll through here, we can sort of see the whole thing of where we started. Hopefully that helps.